Hello chemists, I'll be doing an in-depth analysis of the Wittig reaction. One of the most useful tools in a chemist's arsenal of reactions. It takes a carbonyl and a Wittig reactant here, which is an ylide, we'll see about that later, and makes an alkene combining the two groups. Alkenes are very useful as they can be halogenated, in this case with a bromine, hydrated, or epoxidized, and a lot more reactions that I do not remember and that are several times more complex than these. To demonstrate the Wittig reaction, I chose problem 12C from homework 12.2, which is a synthesis problem. We have a benzene molecule with an O-methyl and an O-methyl and an aldehyde. Pretty simple. And that is added to some sort of cyclopentane with a carbonyl, and that makes this. But how is the question? That process, well, we can assume this is a Wittig because it's an alkene, and it's also Wittig's lesson. So we're going to assume at the last step, because this remains unchanged, these O-methyls remain unchanged, we're going to assume it's a Wittig, and just roll with it. The first step is a reduction. The two reductions we could use are sodium borohydride or lithium aluminum hydride. Those two are very similar. As you can see, both of them have alkali metals, such as sodium or lithium, and they have a group 13 metal that is negatively charged. I'll just show it on the periodic table. Group 13 have 3 valence electrons. If you're going to do formal charges, because these are negative, let's just write this out. They have, we'll just assume that we don't know what their formal charge is. They have 3 minus 4 minus 0, because there are 0 dots on these. That's negative 1. Thus, we get a negative charge on these. While I would love to explain the mechanism for how you do a reduction with either of these molecules, it's a bit unique compared to the stuff we've learned in Orgo 1 and Orgo 2, as it involves metals, and metals act different in terms of normal chemistry. As our next step, I'm just going to show you what happens. This forms a secondary alcohol, which I have covered up for the sake of a more interesting lesson. Let me just make this a little bit bigger so that we can get a nice and quality eraser. Ta-da! A secondary alcohol. From this, we're going to instantly brominate it because that gets us to an alkyl halide, which we can then use to make our Wittig reaction. So, phosphorus tribromide, ta-da! Let's just follow the arrow with our alkyl halide to prepare the Wittig reagent. Sorry, this program is not exactly built to have videos. I drew out some of the mechanism already for the sake of time. The first couple points I'll notice is that here's the alkyl halide that reacts with a triphenyl phosphine. This triphenyl phosphine attacks a leaving area. Well, sorry, let me restate that. The bromine leaves as the first thing. It's a leaving group. It's what it does. And this lone pair on the triphenyl phosphine attacks the carbocation in an SN2 reaction. That SN2 then forms what is called a phosphonium salt. I have things covered up here. It's a little way to make this lesson more interesting, to uncover things. It's more fun. In this situation with the phosphonium salt attached to the cyclopentane, it undergoes not an elimination, but a carboanion formation. Any sort of base would work here, but in the instance I chose, potassium hydroxide. The potassium ion is a spectator ion. It's not particularly relevant. However, the hydroxide, the negatively charged oxygen, takes one of the hydrogens to form an H2O. Sorry for my horrible drawing. That then has the sigma bond between the carbon and the hydrogen go onto the this tertiary carbon. Go onto this carbon, and that makes a negative charge. This is an ylid. An ylid is when you have a positively charged group and a negatively charged group adjacent, which, for understanding this better, I'll just say is one bond away. It can be a double bond or a triple bond, just as long as they're one bond away between these two things. You might ask, yeah, ylid, what is that? A little bit to explain the concept. A great scientist a while ago discovered a zwitterion. A zwitterion is a molecule with separate positively and negatively charged groups. As you can see here, this has a separate positive and negatively charged group. But they're adjacent. Of course, there are different terms because chemists love to make specifics. If it's adjacent charges, it's an ylid, which is what a Wittig uses. If it's non-adjacent charges, it's a beta-ene. Yeah, Wittigs are reactions that use it. They're pretty neat. What about beta-enes? What's the point of those? It's a word. Why make it? Zwitterions are not just something mentioned for Wittigs and nowhere else. They are fundamental for amino acids. You know, the stuff your bio teacher made you memorize, and maybe like that one unit where you forgot the stuff before a test, got them confused a bit. That is essential to life functions, and they have zwitterion forms. I'll get to that later if I have time. Anyways, here's the Wittig reactant. We've made a Wittig reactant. Oops, sorry. And here is where I started. Let me uncover it. The first thing we do is that we have reactant A, the one we didn't touch, the one we just say we leave as is. That undergoes an attack from the carboanion. You can see here. The carbonyl's pi bond goes up to the oxygen, making a negatively charged oxygen and opening this to become a positively charged carbon. That negatively charged carbanion attacks that carbon and combines it. Oops, too much. The next step is interesting, as how I mentioned beta-enes are not just something for the fact of them existing. Beta-enes are also relevant, and beta-enes are a part of the Wittig reaction. They are interesting as they have both ylids and beta-enes as part of their mechanism. Let me just cover this up a little more. It's fun to uncover things. It's like when you have I Spy or some sort of hide and seek and you finally find the person. Anyways, here the benzene and oxymethyls, they're untouched. Here, hydrogen, same thing as before. Here's the negatively charged oxygen, and this is the important part. This carbon makes a bond between those, as you can see right here, and this negatively charged oxygen attacks the phosphorus. Phosphorus, let's remember what phosphorus is. We go back to the periodic table. Phosphorus is in the same group as nitrogen. They have 5 valence electrons. Something with 5 valence electrons is going to want either one bond, nitrogen for example, it's going to want one lone pair and 3 bonds, or 5 bonds, which is not as common, but definitely possible. In this situation, the phosphorus, as it's a bigger molecule, it can make 5 bonds. This forms a very interesting intermediate known as an oxaphosphetane, which is a 4-membered intermediate. This is what the group looks like overall. It's a very interesting square structure. OXA phosphetane. Dun, 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 dun. Let's zoom in on this a bit more. To explain what happens here, the oxaphosphetane intermediate does not stay around for very long. This 4-membered ring, while it is possible, is not preferable. However, the atoms here can make a very stable molecule known as triphenylphosphine oxide, where there is a double bond between the oxygen, and we know from what a Wittig does is that it makes an alkene. So, to get to that point, the sigma bond between the carbon and the oxygen has to break, and that goes up to form the triphenylphosphine oxide. For the phosphorus to leave, that is going to then make the alkene. Let's just think about what happens here. This phosphorus is going to have 1, 2, 3, 4, and a 5th bond. So it's going to be happy. This oxygen has 1, 2, 3, 4 electrons on it currently, and it's going to make double bond, so it'll have it'll have 1 bond, 2 bonds. Both of them have satisfied octets and make a very stable solution, or very stable side product. This is the end of the Wittig reaction. While we make something pretty simple, honestly, it's not that complex of a mechanism. Here it is. The reaction we made initially, and we can say we are done. Here is the final product. Let's go back to here. Same thing. Same situation. However, let's think about this a bit more. To you special chemists, you might think, but why is it like this? Why can't it be like this, going down, and make this? Sorry for horrible drawing. That is because the Wittig is the selective. Sorry for the horrible accent. The point is that a Wittig is always going to make a Z alkene, or better known as a cis alkene. Oh yeah, forgot to mention, for you special chemists who did remember about the ZE cis trans alkenes thing, I have a gift for you. Quarantine edition. Give me a little minute to find it. I have it hidden in this file very, very well. You can't particularly see it, but it's a very small quarantine cookies. So here, take a cookie. Good enough? Okay, back to the lesson. While this is pretty good, also I should mention that here I just had the side product listed. While this is the end of the lesson, I want to go into more trivia and explain what happened with this amino acid zwitterions thing. My friend Chris, as I'm going to medical school, I want to become a doctor. My friend Chris currently is in medical school. He told me about a bunch of stuff that he's learning, like how to memorize the amino acids, and he's going to take the MCAT. For the MCAT, you need Orgo Chem. So he's like, oh, you're taking Orgo? Neat, what stuff do you know? And he asked me about amino acids and said a really simple fundamental question. Like, something about glycine and whether it's acidic, basic, neutral, an aminophile, whatever. I did not understand a word of what he said, but I did understand the word amphoteric, because water is amphoteric, and he said that's what the answer was. Here is a rough recreation of the question. This is the point. He called it a freebie, because for him it was extremely easy. Glycine is best described as an acid base, a neutral compound, amphoteric compound, or an aminophile, which an aminophile is apparently nonsense for this question, but it's what he told me. Anyways, let's look at glycine itself, the molecule, what it actually is. Glycine is one of the simplest amino acids. In terms of amino acids that exist and that are used in, biochem, it's pretty simple. Here's your amine, here's your acid, only one carbon away. It's a precursor to many proteins, the big unfolded 3D structures your bio teacher says are like some of the highest levels of proteins and, not proteins, highest level of molecules that can be made. And in these situations, while by itself it does act as a precursor, it actually works in the brain. Here's, that's a very bad drawing of a brain. It acts as a neural inhibitor. And, interestingly enough, because it's as a simple molecule, it was one of very few molecules that were amino acids discovered off of Earth in 2009, which leads quite to the theory that there is life on other planets. Anyways, let's get going. Here is the glycine. Here has a nitrogen with 2 electrons, a lone pair that's very electronegative. This lone pair does normally it would do an intermolecular attack and do a hydrogen transfer. But in this case, we do it intramolecularly because it's easier. It attacks this hydrogen, that bond between the oxygen and the hydrogen goes onto there, making a positively charged nitrogen and a negatively charged that. But remember what I said about betaines? It's a betaene. Remember how amino acids by their name are an amino acid? They have the same property. Many of them undergo things like this. And I'll just, for time, I'll explain this. This is the glycine's Vitter ion that we just got with This is the glycine's Vitter ion we just got with a positively charged ammonia and a carboxylate that is negatively charged. It is neutral. Little things I wrote down. If we were to lose this hydrogen, then it would become very basic, as this is negative and wants a hydrogen, and this is negative and wants a hydrogen. So it is high pH basic and is a glycinate anion. Let's go the other way. If we were to protonate this and have an H and this becomes neutral, then we would have a very, very protonated thing. It could lose an H here or here. It is very acidic. Acids are proton donators. So it is low pH, acidic, and this glycinium cation is very, very acidic. This glycine has 4 forms. The very beginning, a hydrogen transfer, a glycinate anion, and a glycinium cation. So it acts neutral, acidic, and basic. So it's amphoteric. Finally, I understand Chris's question and why it's so rudimentary. Amino acids all have this property. So saying it's an acid is wrong. A base is wrong. Neutral compound is wrong. And it's best described as it's amphoteric, as it's all of them. Every molecule in your body that's an amino acid is a Vitter ion. The Wittig reaction likely happens in your body. Well, maybe I cannot guarantee that, but You have likely encountered some molecule in your life, be it from coffee, prepackaged candy, something in your life that has had the Wittig reaction and Zwitter ions go through that process to form, I don't know, some sweetener, some preservative, anything. You've probably experienced some sort of Zwitter ion in just the mechanisms to get to that point. What I'm trying to say is, all this babble about Zwitter ions is not nonsense. It's in your body. You've experienced it. You've tasted it. And it's real. And it makes up everything in you. Chem's pretty cool. That's why I like being chem. And I'm the alchemist. This is my thing. See you around.